welcome to the next lecture on wireless communications. This is the second part of our lectures on GSM and CDMA. Today we will focus our attention on CDMA technologies. First, the outline of today's talk. In this talk we will learn about the CDMA signal generation, the types of codes used in CDMA, forward and reverse link code channels, and finally CDMA call processing. So exactly what we want to learn in this part of the lectures is how CDMA systems work. CDMA of course stands for Code Division Multiple Access, but it is much more than just a multiple access scheme. There is a lot of inherent technologies embedded into it, which we call together as CDMA. So the words code and division are important parts of how CDMA works. CDMA uses codes to convert between analog voice signals and digital signals. CDMA also uses codes to separate or even divide voice and control data into data streams called channels. So the basic idea is to have some kind of a spreading code, which is usually generated using a PN sequence, which converts the basic voice signals into digital signals and uses these codes to have separate channels. These digital stream data channels should not be confused with frequency channels. It is completely different. We have another dimension in space, the code axis. So let us now talk about generating a CDMA signal. There are 5 essential steps in generating a CDMA signal. First of all, we have to go from our analog world to the digital world, so we have to do an A to D conversion. Then an important step where a lot of emphasis is paid in CDMA systems as compared to GSM systems is the voice coder or the vocoding part. Then we move on to encoding and interleaving, channelizing of the signals, and finally conversion of the digital signals into RF or radio frequency signals. So we will talk about all these 5 points from the perspective of CDMA systems. Please note, the use of codes is a key part of this process. So here is a rough block diagram of how the CDMA transmitter part works. You have an analog voice, as you can see, and then you go through an A to D converter followed by a vocoder, then a forward error correction, then you have a channelizing block, and then you have D to A converted into RF and radiate out. So this is the generalized block diagram of a CDMA system, how to generate a CDMA signals. We will focus individually into all of these blocks now. First, the analog to digital conversion. Clearly, the first step of CDMA signal generation is analog to digital conversion, clearly called A to D conversion. Now, CDMA uses a technique called the PCM or the pulse code modulation to accomplish this A to D conversion. That is a standard, but PCM can have different number of bits per symbol, and so we will talk about those also. The second step of CDMA signal generation is voice compression. Now, CDMA lays a lot of stress on this compression part. CDMA systems use a device called vocoders to accomplish voice compression. The vocoder term is a contraction of the word voice and coder. Vocoders are actually located at the BSC and in the phone. So these are the 2 places where the vocoders are located in CDMA systems. A slide on how compression is actually carried out. So here is a diagram of your analog speech. So you talk for some time, then there is a pause, it could be a pause between the words, and then you talk for some more time, and then there is another speech, there is a pause in the speech, and then another section, a burst of data. So this pause could be the pause between words, or the speaker might be thinking. This is wasted bandwidth in GSM. We have to do something about it in order to use this vacant spots, and that is where the CDMA compression system kicks in. So, people pause between syllables and words when they talk, and then think while talking, so they are natural pauses. CDMA systems takes advantage of these pauses in speech activity by using a variable rate vocoder. This is important. So, it is a variable rate. Okay. What is a variable rate vocoder? A CDMA vocoder varies the compression of the voice signal into one of the 4 data rates based on the rate of the user's speech activity. So, if the person is continuously talking, then I will use a different kind of rate, and if there are lot of gaps in the speech, then definitely I will have a much lower data rate. So, it is matched to the speech activity of the speaker. The 4 rates are the full rate, half, 1/4 and 1/8. So, when a person is continually talking, then you use the full rate vocoder, and when there are deliberate gaps in the speech, then you go by 1/8. The vocoder uses its full rate when a person is talking very fast. It uses 1/8 rate when the person is silent or nearly so. Let us now cast our attention on the various types of vocoders. So, CDMA systems can use either an 8 kilobits per second or 13 bytes per second vocoder. Recently, the CDMA community adopted a new 8 kbps vocoder. This new vocoder is actually referred to as the EVRC, or the extended variable rate coding. What it does is it combines the quality of 13 kbps vocoding with the capacity of 8 kbps data rate. So, it is a more enhanced version, the extended variable rate vocoding. We now move to the next part of the CDMA signal generation part, which is encoding and interleaving to take care of the randomness in the channel. Please remember, we are dealing with a hostile environment channel wherein there is multipath, there is shadowing, and then there is additive white Gaussian noise. Encoders and interleavers are built into the BTS and the phones. So, they exist both at the base stations and the handheld phones. Clearly, the purpose of encoding and interleaving is to build redundancy into the signal, so that information lost in the transmission can hopefully be recovered back. In our previous lectures, we have spent a lot of time talking about different kinds of channel coding and interleaving. Just a very simple example to refresh our memory how encoding works. The type of encoding done at this stage is the convolutional encoding. A simplified encoding scheme is a repetition code. This is just for illustration, it is not used. Each bit can be repeated 3 times. Each encoded bit is called a symbol. The decoder at the receiver uses a majority logic if you are doing a repetition code. We have gone in details about linear block codes, cyclic codes, and convolutional codes in our previous lectures. Thus, if an error occurs, the redundancy can help recover the lost information. Now, we realized that in mobile channels, when we undergo fades, we tend to have burst errors. What are burst errors? Burst errors are sequence of bits in error. So, it is not random errors sprinkled all over the data stream, they come in bunches and they are known as burst errors. A burst error is a type of error in the received digital telephone signals. Burst errors occur in clumps of adjacent symbols. These errors are caused by fading and interference. So, suddenly if I move into an area where there is a deep null in the fading profile, I encountered burst errors, or if I move in a region where suddenly there is a lot of interference coming from one of the interfering base stations, I again lose lot of bits in a sequence. Encoding and interleaving reduce the effects of burst errors. CDMA systems employ strong burst error correcting techniques. Now, let us talk about interleaving. Interleaving is a simple yet powerful method of reducing the effects of burst errors and recovering lost bits. So, in the example here, the symbols from each group are interleaved or scrambled in a pattern that the receiver knows. A very simple way is to have a lot of memory. You read in the data row wise into the memory and read out the data column wise. At the receiver side, you put in the data column wise and read out row wise, so that you undo the effect. But what will happen is all the burst errors will then get distributed over the data sequence. But that is just one of the simple ways. Actually, we can use any special kind of scrambling before sending the data and then unscramble the data at the receiver so as to distribute the burst errors. So, we can have various kinds of interleavers: random interleaver, semi-random interleaver, chaotic interleaver, and a host of other kinds of scramblers. De-interleaving at the receiver unscrambles the bits, spreading any burst errors that occurs during the transmission. So, this is the general philosophy how interleaving works. The next step in CDMA systems is channelizing. The encoded voice data is further encoded to separate it from other encoded voice data. The encoded symbols are then spread over the entire bandwidth of the CDMA channels. This process is called channelization. The receiver knows the code and uses it to recover the voice data. So, every channel uses its own PN sequence to spread the data, and the receiver de-spread the data. So, let us consider a simple example when there is a user 1 and user 2, and they use their own PN sequences, codes here, code 1 and code 2, to send their own data. But please note, CDMA system is using the entire bandwidth all the time for both the users. So, clearly they are interfering with each other, intentional interference. But at the receiver, if you use the code of user 1 to decode, you dispread your own signal, but spread further the signal received from the interfering user. Thereby, you obtain the useful data for yourself. CDMA uses two important types of codes to channelize users. One is the Walsh code, the other is the pseudo-random noise or PN codes. Walsh codes channelize users on the forward link, that is base station to mobile. There you have the luxury of more power, right? Whereas PN codes channelize users on the reverse link, that is from the mobile to the base station. There we depend on the battery power, and we do not have the luxury of unlimited power. So therefore, you need to use two different kinds of codes based on the efficiency and performance. Walsh codes for the downlink or the forward link, PN codes for the uplink or the reverse link. Walsh codes. Walsh codes provide a means to uniquely identify each user on the forward link. What is the property of Walsh codes? They have a unique mathematical property that they are orthogonal. In other words, Walsh codes are unique enough that the voice data can only be recovered by a receiver applying the same Walsh code. It's almost close to orthogonal. Very good autocorrelation and cross-correlation properties. So the basic idea of any good code is that when you correlate it with your own code that is autocorrelated, you get a strong peak, and when you cross-correlate it, you get a very low value. So what happens is all the other signals are discarded as background noise. PN codes. PN codes uniquely identify users on the reverse link. A PN code is one that appears to be random, but actually it isn't, hence the pseudo part. The PN codes used in CDMA yield about 4.4 trillion combinations of code. So what does it do apart from channelizing? It is making the system highly secure. This is a key reason why CDMA is also very secure. Inherent advantage of CDMA over your GSM technologies. In GSM, we have to use stronger and stronger codes, authentication codes and other kinds of cryptographic codes to ensure security. Question?
Sir, this PN code is fixed for each and every mobile?
Question being asked is the PN code fixed for every mobile, right? The answer is we have a set of PN codes. Just like in GSM, depending upon when you wish to make the call, you are assigned a frequency and a time slot. Here, you are assigned a particular code when you wish to make a call. So if your phone is on but is in the standby mode, then your code can be given to somebody else. Okay? So a code is not fixed or locked. Also, when you move from one base station to another, then you may have to switch between codes. Right?
So my mobile is given a code during the transaction. When I call, my code is also transmitted as a signal to the receiver side.
Question being asked is, how is the communication set up between mobile and the base station as to which is the code being used? So in the handshaking phase, before the call actually starts, it is decided, apart from the synchronization and power control issues, on the control channels which PN code will be used, and only that one will be used for the entire duration of the call with that particular base station. If you move to the other region, in the handoff process, your code will be changed.
So also why we are using vocoders at both the mobile and the base station, because base station only has to transmit that information.
Question being asked is, why are vocoders being used at both the base stations and mobile stations? Vocoders' purpose is to compress. So it doesn't matter. Speech, for example, has a lot of inbuilt redundancy because of pauses. So that makes the use of vocoders justified. You are packing in a lot more information.
So but in the mobile it's only necessary.
Speech is coming from both the mobile, the speech communication is two-way. So it is required to use the vocoders. If there is a PSTN to a mobile call, then also we need to use the vocoders to compress it. So it is built in to the standard.
Sir, two mobile stations have the different type of set of PN codes.
Question being asked is, do two different mobiles have different set of PN codes?
Two mobile stations, base stations.
Yeah, yeah. So the answer is two different base stations may have different sets of codes which will be assigned to the mobile, and when the mobile goes from one base station to the other, then there will be a handoff of the codes. So you negotiate again, decide on the control channels which next PN sequence you are going to use, and then continue your conversation. The final stage into generating the CDMA signal is the digital to radio frequency or RF conversion. The BTS combines channelized data from all calls into one signal. It then converts the digital signal to the RF signal for transmission. Now, we move to the receiving end. So, from base station we go to the receiver. After the CDMA signal is transmitted, the receiver must reverse the signal generation process to recover the voice as follows: conversion of RF to digital signal, despread the signal, deinterleave and decode, voice decompression, and finally digital to analog voice recovery. Just the reverse of the process. If all of them work well, we hear the voice with clarity. So, the receiver block diagram looks like follows. There is an antenna and then there is a D2A RF. It goes to the despreader. Then you have the forward error correction module followed by the vocoder, A to D, and your recovered voice signal. So, this is the rough block diagram of the CDMA receiver. Of course, you need to have a code generator in order to despread. Which code is being used is pre-decided during the conversation. If I go from one base station to other, then this code generator will switch from code 1 to code 2. A code channel is a stream of data designated for a specific use or person. This channel may be voice data or overhead control data. Please note, in CDMA also we need a lot of control channels as well as traffic channels. Channels are separated by codes, hence this is the CDMA system. The forward and reverse links use different types of channels. First, the forward link channels. The forward link uses 4 types of channels to transmit voice and control data to the mobile. Please remember, forward link implies base station to the mobile. The types of forward link channels are pilot, sync, paging, and traffic. As the name suggests, all 4 are meant for different purposes. What does the pilot channel do? The PTS, our base station, constantly transmits the pilot channel. The mobile uses the pilot signals to acquire the system. It then uses the pilot signal to monitor and adjust the power needed in order to transmit back to the base station. Please note that CDMA systems rely heavily on power control. So, the CDMA system can be compared within this room to a very simple example that all of the students in the room are talking in a different language. So, English, French, German, Tamil, Hindi, and I as the teacher am able to understand all the languages. So, each language forms a code and all of the users are talking at the same time. The base station, which understands all the languages, can uniquely decode each of the languages. So, all the users, which are the students in this class, are using the entire bandwidth all the time, right, but using their own code, which is the specific language, to talk. But what is important is the student sitting in the first row must speak softly. otherwise they will drown the sound coming from those sitting at the back bench. So, the users which are closer to the base station must transmit at lower power. Those at far away must use a higher power. Who will decide how much power to use? This has to be decided by some kind of a control channel, and pilot channel is used to do that. So, please remember, this is the near far problem in CDMA system, where there is a threat of a mobile close to the base station drowning the signals coming from a mobile far away from the base station. Hence, power control is essential for the proper working of CDMA systems.
So one more question. So if the sender and receiver are using the code and during that a handover occurs from one base station to the other, should the same code is used or the other?
The question being asked is, while a conversation is going on, suppose the mobile moves over to another base station and a handover is started. So, is the same code maintained or not? So, the answer is most likely not, because even though that code may be available in the next set, it may be already being used by some other user. So, invariably you will be assigned a new code to talk while you are within the domain of the next base station. So, the code will change. Sync channel. The BTS constantly transmits over the sync channel so that the mobile can synchronize with the base station. Please note, the PN sequences are good only if your time reference is good. Even if you shift the PN sequence slightly with respect to the original PN sequence, the autocorrelation will go bad. So, synchronization is of utmost importance. It provides the mobile with the system time and the identification number of the cell site. So, it is primarily used for time synchronization. The mobile ignores the sync channel after it is synchronized. So, it transmits a set of known patterns by virtue of which you synchronize, basically lock in. Paging channel, the name suggests, is used for paging a mobile. CDMA uses up to 7 paging channels. The paging channel transmits overhead information such as commands and pages to the mobile. The paging channel also sends commands and traffic channel assignment during call setup. So, each time we are talking about handover, this call setup must be initiated. The mobile ignores the paging channel after a traffic channel is established. What do we mean by traffic channel? Once the voice communication starts, right, the paging channel is no longer required. Forward link traffic channels. CDMA uses between 55 and 61 forward traffic channels to send both voice and overhead control data during a call. These funny numbers come up because we need certain number of orthogonal codes. If you increase the number of codes, you have to increase the length of the codes to ensure that their proper orthogonality remains. But there is an upper bound on the length of the code we can put for real time voice communications. So, these numbers like 55 and 61 number of channels come out. They are limited by the number of orthogonal codes that are available. Once the call is completed, the mobile tunes back in to the paging channels for commands and pages. So, it is like a state diagram. So, either it is in a traffic mode or it is in the wait state tuned into the base station waiting for the commands. Let us now talk about the reverse link channels, the channels provided from the mobile to the base station. The reverse link uses two types of channels to transmit voice and control data to the base station. The types of reverse link are access and traffic. Now, what do we mean by access channel? The mobile uses the access channel when not assigned to a traffic channel. The mobile uses the access channel to do the following. First, it has to register with the network. So, the moment you switch on the phone in any territory, you have to register with the user, with the network, to tell, okay, I am there, I can be paged later on. Access channel is also used to originate calls, respond to pages and commands, transmit overhead messages to the base station. Now, the reverse link traffic channel is used only when there is a call. The reverse traffic channel transmits voice data to the BTS. It also transmits the overhead control information during the call. So, let us see how it works. There is an initialization and then there is an idle mode. It can go to the access mode. If there is a call initiated, you go to the traffic mode and then go back to the idle mode once the voice communication is over. So, this is the basic state diagram for the call processing at the mobile. So, there are 4 stages or modes in the CDMA call processing: initialization, idle, access, and finally traffic mode. Let us talk about these modes. During initialization, the mobile does the following. It acquires the system via the pilot code channel, and then it synchronizes with the system via the sync code channel. Clearly, you need to set your transmit power information correct and your time synchronization correct. Once these two are there, you are all initialized, rearing to go for any request for a voice communication. Needless to say, these have to be updated periodically. The idle mode. This is when the mobile is not involved in a call, but it must stay in communication with the base station, and clearly it will expend some battery power. The mobile and the base station communicate over the access and the paging code channels, and the mobile obtains overhead information via the paging code channel. At this time, there is no voice communication taking place, simply because there is no request for voice. Now, the access mode. The mobile accesses the network via the access code channel during call origination. The access channel and the paging channels carry the required call setup communication between the mobile phone and the BTS until a traffic channel is established. So, you exchange information on what kind of code will be used. Right? The power is already set up, and once these basic requirements are put together, we try to move to the next mode, which will be actually the traffic mode.
Sir, in ideal mode, base station will assign the PN code also to the mobile user. Like, it means that all the time the mobile user has the PN code.
Okay. The question being asked is, in the access mode, does the base station assign the PN code? The answer is yes. During this mode only, a mutual agreement is there as to which code will be used. So, it has a set of codes, but which one to use will be decided during this access.
All the time, like in the ideal mode it will be.
No, in idle mode the code is not decided. At that time, we only talk about the power that I require to use and the time synchronization. Time synchronization is important even to carry out the communication regarding which PN sequence to use, because all the communication is being done based on codes. Right? So, timing and power are essential requirements for communication, not necessarily voice, even control information. Therefore, if you go to the idle mode and initialization mode, here you must acquire the system and maintain the synchronization, because communication is required even to communicate which PN sequence to use.
So, but for this communication again there should be some code.
Yeah, those are pre-decided. So, the codes required for idle channel, that is for communicating, synchronizing, right, acquiring the system, those are pre-decided. So, when you switch on your phone, you already have them hardwired. So, we come back to traffic mode. So, during a LAN to mobile call, the mobile receives a page on the paging channel. The mobile clearly responds on the access channel. The traffic channel is established and is maintained throughout the call. So, the same PN sequence is maintained. During a mobile to landline call, the call is placed using the access channel. The base station responds on the paging channel, and the traffic channel is established and maintained throughout the call. Call processing for messages. During the call, overhead messaging continues on the traffic channel in a limited fashion. So, please note, even though your call is being made, overhead messaging continues in parallel in a limited fashion. The message uses dim and burst or blank and burst signaling, which replaces part of the voice traffic with system messages. The user does not detect this signaling, however, due to the strong data recovery schemes inherent in CDMA. As we discussed before, CDMA has bifurcated and comes in two flavors today: the CDMA 2000, which was originally proposed by Qualcomm, and the WCDMA standard. So, there has been an ongoing debate which finally has not been resolved, and so we now have two 3G standards, the CDMA 2000 standard and the WCDMA. The CDMA 2000 standard had to be different because Qualcomm owns about 200 key patents here which cannot be violated, and it is also too expensive. So, WCDMA independent standard also exists. What we will try to do is look at the differences and similarities between these two standards very briefly. In India, we are following CDMA 2001X. So, in this table, we have the various parameters. For example, look at the chip rate. Chip rate is defined as the minimum chip interval used in the spreading codes. Chip rate is much smaller than the bit rate. The smaller the chip rate, the more the signal will be spread. Now, CDMA 2000, for example, uses 3.68 mega chips per second, whereas WCDMA uses 4.096 mega chips per second. There is no reason why they have to be different. Right? So, these are minor differences. If you look at the downlink pilot for channel estimation, it is using CDM, common pilot, whereas WCDMA uses TDM, dedicated pilot. Antenna beamforming, you have the auxiliary pilot, whereas here TDM, dedicated pilot, is used for antenna beamforming. What about the synchronization? In CDMA 2000, we have synchronous, whereas in WCDMA it is asynchronous mode of synchronization. Acquisition and detection of the base station, here the synchronization is through time shifted PN sequence, whereas in WCDMA you have an elaborate 3-step parallel code search method. So, these are some differences which come out between CDMA 2000 and WCDMA. This table has been put up just as an illustration of some of the differences which are there. You can have several slides just to delineate the differences between CDMA 2000 and WCDMA. Of course, there are a lot of similarities also. So, you have coherent forward link and reverse link in both. You need fast power control in forward link and reverse link. It is an essential requirement of all CDMA systems. You have variable length orthogonal watch sequences used for forward link channelization. you have complex QPSK spreading on forward link and reverse link. This is identical for both systems. Identical polynomials for convolutional codes, or very similar polynomials for convolutional codes. Then you use parallel turbo codes for higher data rates. Of course, as mentioned before, we use CDMA 2001X EVDO in India. Some more similarities: variable spreading factors to achieve higher data rates, mobile assisted inter-frequency hard handoff procedures, variable rate operations with blind rate estimation for simple services like voice. So, we have already talked about the variable rate operations in the vocoders before. Continuous reverse link operation. Now, let us have certain slides on error control codes from the perspective of these wireless standards. We have already had an in-depth study of various error control coding techniques. This is revisiting from the perspective of wireless standards. So, clearly our mobile radio channels have high bit error rates, as bad as 10 to the minus 3 to 10 to the minus 1 uncoded, whereas the acceptable is between 10 to the minus 5 and 10 to the minus 7 bit error rates. Now, in CDMA we have already compressed our data, we have already thrown out the redundancies. So, we must make it robust to errors. The highly compressed speech data and fast data communication is not possible without very good error control codes. It is an absolute must. So, sophisticated error control schemes, both block and convolutional, are used for channel errors, and interleaving is used for burst error correction. Error control codes for GSM. The GSM system uses the following. It uses block codes to generate parity bits for error detection, convolutional codes for error correction, and interleaving for burst error correction. So, you start in a digital domain, you go through a block code, you add a parity, convolutional code lengthens the sequence further, and interleaving reads it into rows and reads out in as columns and breaks up the data. Speech data is classified into the following classes of varying importance, are encoded accordingly. So, there is a class 1, class 2 and class 3. Class 1 is the most important and constitute 50 bits out of the 260 in each speech frame. These describe the LPC filter coefficients and amplitude information. Similarly, you have the class 2 definition, which constitute 132 out of the 260 bits and carry information for long term prediction coefficients LTP, whereas class 3 there are 78 out of the 260 bits and contain regular pulse excited RPE parameters. So, these are some basic types of speech data classification. Speech data occurs on the TCH, which is the traffic channel for the payload data in speech frames of 260 bits. Okay. So, this 260 bits is coming on the speech frame. Of these, 182 bits are error predicted and the remaining 78 are not, and the following cyclic redundancy check CRC code polynomial is used for GSM. For class 1 codes, we have block coding with a CRC used only for error detection. This is done by adding 3 parity check bits. If the decoder detects an error in class 1 bits, the entire block is abandoned and retransmission is requested. So, it is a scheme where you request for retransmission of data once the error detection takes place. CRC, we know, is an important class of error detecting codes. The convolutional code is applied to both class 1 and class 2 bits, including parity bits generated from class 1 bits. The convolutional code used has a rate 1 by 2, and the transmission errors can be compensated to a certain degree in speech decoder by extrapolation. The discarded or missing frames are extrapolated from the data from the last valid speech frame, those detected without errors. Now, that was speech. We have block coding for data traffic, which is more sensitive to errors. Data traffic must be protected better than speech data, okay, because our ears are not so sensitive. We can internally extrapolate and figure out the missing words. At most, there will be a crackle in the sound. We can still make out what is going on. But in data, if we make more than the possible errors that can be detected, then we are in soup. Extra bits are added by rate half convolutional encoder. For example, for 9.6 kilobits per second user data rate, we need to transmit 12 kilobits per second because of the addition of redundant bits. Again, for 2.4 kilobits per second user data, we need to transmit 3.6 kilobits per second because of the redundant bits. In this case, no parity bits are determined. Block coding is done based on data rate, whether it is full rate or half rate, as well as the channel type. So, you have to do something to estimate how bad the channel is. Data is broken up into different sized blocks depending upon the data rate prior to coding. Block coding for signaling channel. Please note that we also have signaling channel. It is important to protect the data being sent over those signaling GSM channels. So, these are the signaling channels which we have studied in the previous class. They must use very powerful block codes for error detection, because if your signaling information goes haywire, then your rest of the information will be useless. So, it is important to protect the signaling channels. Fire codes are used. So, probability of undetected error is very high. It is a very strong course. In our series of lectures, when we talked about cyclic codes, we studied fire codes in detail. So, fire codes are used, which will guarantee you probability of undetected error of 10 to the power minus 12. Fire codes can be defined as the CRC using this following generator polynomial. GSM defines different generating polynomials for different channels. All have the constraint length 5, and here are 4 examples of the different kinds of generator polynomials used for different kinds of channels, right. So, clearly by looking at the highest power of x, which pertains to n minus k, right, you can know what is the length n and k, and also you can find out how many errors these can correct. Those were the codes for GSM. Now, let us discuss the codes used for CDMA systems. In the reverse link, which is defined as the mobile station to base station, and please note here we rely only on the battery power. So, we cannot afford to have very strong signal power. The mobile station convolutionally encodes the transmitted data prior to interleaving. Interleaving is a must, because convolutional encoding is also useful not for burst error, but for random errors. So, interleaving will make burst error look like random errors. The convolutional coder has a rate 1 by 3, which is a stronger code than the rate 1 by 2 encoders. We are putting in more redundancy. And also note the constraint length of 9. Clearly, we are anticipating more errors in the reverse link channel, and hence using a stronger code. Just for the sake of description, the generator function for the codes are given in the octal format as follows. The code symbols constitute the output so that C0 is generated using G0, C1 is using G1 and C2 generated using G2. What are C1, C2 and C0? They are the 3 output bits, because your rate of the convolution encoder is 1/3. So, for every 1 bit that goes in, 3 bits get out. The code symbol repetition rate on the reverse channel with the data rate for IS-95 are as follows. For 4800 bits per second, it's repeated once, 2400 repeated 3 times, 1200 repeated 7 times. The repeated code symbols are then fed into the interleaver. This is an example picked up from the first generation CDMA system, which is the IS-95. Let us talk about the base station, the mobile station. The convolutional encoder used with data rate of half. So, it is a weaker convolutional encoder as compared to the rate 1/3, but the same constraint length. So, for every 1 bit that goes in, 2 bits get out of the encoder. And how are they defined? They are defined using these 2 generator functions in octal. Codes are repeated for the sync channel and the paging channel. After repetition, the codes are passed on to the interleaver. So, let us now summarize what we have learned in today's class. We started off with CDMA signal generation. Then we talked briefly about the types of codes that were used in CDMA systems. We then separately discussed the various kinds of forward and reverse link code channels. What are they used for? How are they different from each other? And then we discussed CDMA call processing. Finally, to put things in perspective, we talked about error control codes and compared the error control codes used for GSM and CDMA technologies. We have seen that block codes, cyclic redundancy check codes and convolutional codes all are used in the various wireless standards. Because the wireless channel is a fairly hostile channel, it is a bad channel and it has to be protected. We also saw that we need to protect the traffic channels as well as the control channels. This brings us to the end of this 2-part lecture on GSM and CDMA technologies. We will conclude our lecture here.